Tonight, somewhere in a quiet corner of the cosmos, a star is glowing so impossibly large that if you removed our sun from the center of the solar system and replaced it with this monster, you would not just lose Mercury. You would not just lose Venus or Earth or Mars. You would lose Jupiter. You would lose the asteroid belt. You would lose Saturn itself, vanished entirely inside the boiling outer layers of a single star. And the strangest part of this story, the part that has rattled astronomers and forced them to redraw their charts again, is that scientists have just found another one. Another contender for the largest object ever discovered in the universe. A star so massive, so swollen, so absurdly large that it almost should not exist by the rules of physics as we currently understand them. By the end of tonight, you are going to see exactly how this new giant was uncovered, why its discovery has reopened a century-old debate about the true upper limit of stellar size, and what it means when nature builds something so enormous that the laws of physics begin to bend just to hold it together. You will see how a single point of light, lost among billions of others in a crowded patch of sky, became one of the most important objects in modern astronomy. And you will see why the answer to the question of how big a star can get is not a number, but a battle. A constant, violent argument between gravity and light, between collapse and explosion, fought across millions of miles of glowing plasma. Before we begin, if you find yourself drawn to the deepest, strangest objects in our universe, take a brief moment to like the video or subscribe to the channel. It is a small gesture, but it carries this work to more curious minds, and that is genuinely how stories like this one continue to be told. Now, settle in. We have a long way to travel tonight, roughly 160,000 light years by the time we are done. To understand what we are looking at, we have to go back, not to the moment of discovery, but to the question that came before it. For most of human history, no one believed stars could have a size at all. They were lights. Tiny, fixed pinpricks fastened to a celestial sphere, as the ancient Greeks imagined it. Even after Copernicus and Galileo shook the foundations of astronomy, even after telescopes revealed that the so-called fixed stars were in fact distant suns, the idea that stars could be measured, weighed, and compared to one another seemed almost preposterous. How could anyone hope to determine the diameter of an object so far away that its light took years, decades, sometimes thousands of years to reach us? It seemed like asking how tall a candle was by standing on the opposite side of an ocean and squinting. And yet, by the late 19th and early 20th centuries, astronomers had begun to do exactly that. Through a careful chain of reasoning that connected brightness to distance, distance to luminosity, luminosity to temperature, and temperature to surface area, they began to assign physical sizes to stars. The numbers that emerged were astonishing. Our sun, which feels overwhelming when it climbs into a summer sky, turned out to be modest, average, a perfectly ordinary middle-aged star drifting in a fairly unremarkable arm of an otherwise unremarkable galaxy. There were stars hundreds of times its size, stars thousands of times brighter, stars so vast that if they took the sun's place, entire planets would disappear into their atmospheres. These extreme objects came to be known as supergiants, and in the most outrageous cases, hypergiants. A hypergiant is not just a large star. It is a star at the very edge of what gravity will allow. A star whose own light is trying to tear it apart from the inside. A star losing mass into space at rates that would horrify any engineer, with stellar winds carrying away the equivalent of an Earth every few months and dust shells stretching outward across entire solar system widths. Hypergiants are rare. They are short-lived. They are violent. And they are the objects that hold the records for sheer physical size in our universe. The current record holder, depending on who you ask and which measurements you trust, has shifted several times over the past few decades. VY Canis Majoris held the crown for a while, then UY Scuti, then Stephenson 218. Each of these stars carries a radius somewhere in the neighborhood of 1 to 2,000 times that of our own sun, meaning their surfaces, if dropped into the center of our solar system, would extend out past the orbit of Jupiter, and in the most extreme cases, past the orbit of Saturn. These were the kings of the cosmos, the largest objects we had ever catalogued, and the assumption, quietly, was that we had probably found the upper limit. that nature could not really build anything much bigger than this without it immediately ripping itself apart. That assumption is now being tested, because in recent years, astronomers using a new generation of instruments, including the Very Large Telescope Interferometer in Chile and the infrared eyes of the James Webb Space Telescope, have begun to peer more deeply into regions of the sky that were previously hidden, star clusters smothered in dust, distant galaxies whose individual stars could only be guessed at. The results have been remarkable. One particular star, sitting in a satellite galaxy of our own Milky Way, has emerged as a candidate for something even larger than what we previously believed possible. Its discovery did not come from a single dramatic moment. It came from years of patient observation, recalibration, and an almost unbelievable image, the first ever taken of a star outside our own galaxy that actually showed its surface as a tiny resolved disk rather than a point of light. That star sits in the Large Magellanic Cloud, a small companion galaxy to the Milky Way visible from the southern hemisphere as a faint smudge in the night sky. The cloud is roughly 160,000 light-years away, far enough that for most of astronomical history, individual stars within it were essentially indistinguishable from one another. They were points, just points, but not anymore. Now, for the first time, we are beginning to see them as worlds, as objects with structure, as stars with surfaces, with shapes, with weather. And what we are seeing is, to put it mildly, unsettling, because some of these stars are bigger than anything in our own galaxy. They are bigger than the giants we thought we had already maxed out. They are stretching the boundaries of what stellar physics is supposed to allow. The newcomer has been studied for decades, but only recently has its true scale begun to come into focus. Earlier estimates placed it among the largest known stars. Newer observations suggest those earlier estimates may have been conservative. If the current numbers hold, this star has a radius that could rival or even exceed the largest known stars in the Milky Way. Drop it into the center of our solar system, and not only would Mercury, Venus, Earth, Mars, and Jupiter be swallowed whole, but Saturn itself, that distant ringed world that takes nearly 30 years to complete a single orbit around our Sun, would find itself buried within the star's atmosphere. The rings would not survive the encounter. Saturn itself would not survive the encounter. The entire region of space we think of as our solar system, out to nearly 1 billion miles from the Sun, would be inside this single star. And this star is not alone. That is the part of the discovery that has really caught the attention of astronomers. Because once you find one object pushing the limits, the natural question is whether it is a freak, a statistical accident, a one-off. The answer, increasingly, appears to be no. There are others, hidden in the same regions, embedded in the same dust clouds, lurking in the same satellite galaxies. A whole population of extreme stars that we have been undercounting and undermeasuring for decades. We are not just discovering one new giant. We are discovering an entire category of cosmic objects that had previously slipped through our nets. So tonight, we are going to walk through this discovery from beginning to end. We are going to look at how astronomers first noticed something unusual. We are going to see what tools they used to confirm it. We are going to learn how they measured a star so distant that its light had been traveling toward Earth since long before anything resembling human civilization existed. We are going to explore what such a star looks like up close, how it survives against its own crushing gravity, why it cannot last more than a cosmic eye blink, and what will happen when it finally exhausts itself and dies in one of the most spectacular events the universe is capable of producing. We are going to talk about why this matters. Why a star tens of thousands of light years away, swollen to a size that defies imagination, is more relevant to your existence than you might guess. And we are going to end with a question that astronomers are now asking with renewed urgency. If we have already been wrong about the upper limit once, how confident can we really be that we are not still wrong now? But to get there, we have to start at the beginning. We have to start with a faint smudge of light in a southern sky catalogue. A star that nobody noticed at first. A star that, for nearly a century, was just another entry in a list of red giants in a neighboring galaxy. A star that almost no one believed could be anything more than ordinary, until someone looked closer. until someone pointed an instrument at it that had not existed in any previous generation, until someone realized that the numbers they were getting back could not possibly be right. And then, when they checked again, they realized the numbers were exactly right, and the implications were enormous. The star at the center of tonight's story is called WOHG64. The name is not poetic. It is not evocative. It is the kind of designation that astronomers assign to objects when they catalogue them quickly, without any sense that the entry will one day become legendary. WOH stands for Westerlund, Ollander, and Hedin, the three astronomers who in the early 1980s were systematically scanning the large Magellanic Cloud for cool, luminous stars. The G refers to a particular field within their survey. The 64 is simply a number, the 64th red object they catalogued in that particular region of sky. Nothing more. There was no fanfare, no press release. No suggestion that this faint red speck, embedded in a dusty corner of a satellite galaxy, might one day be a candidate for the largest known star in the local universe. For decades after its initial cataloguing, WOHG64 remained a curiosity. Astronomers knew it was unusual. They could tell from its spectrum, from the way it shone in infrared, that this was not a typical star. It was clearly cool, clearly red, clearly enormous in some sense. But how enormous, exactly, remained a question that no instrument of the time could properly answer. The large Magellanic Cloud is, by cosmic standards, a neighbor. Yet 160,000 light-years is still 160,000 light-years. The individual stars within it, even the brightest and largest ones, appear from Earth as nothing more than points, pinpricks of light. You cannot resolve them. You cannot see their shape. You cannot, in any meaningful sense, image them as objects. They are inferences. They are calculations. They are conclusions drawn from clever analysis of light, not direct observations of structure. This is the central challenge that has haunted stellar astronomy from its earliest days. Stars are far. Stars are small in angular terms, no matter how huge they are in physical terms. A star with a radius 2,000 times that of our Sun, sitting at a distance of 160,000 light-years, subtends an angle so vanishingly small in our sky that for most of history we did not even have the language to describe how small it was. We are talking about angles measured in milliarcseconds. That is, thousandths of an arcsecond. And an arcsecond, for those who have not spent time with this unit, is 1/3600th of a degree. Take the full moon, divide it into thousands of slices, and one of those slices is roughly an arcsecond. Now take that arcsecond and divide it again by 1,000. That is the kind of angular size we are talking about for a star like WOHG64. To measure something that's small from across that much space, you cannot just point a telescope at it and snap a picture. Even the largest single telescope on Earth, even the Hubble Space Telescope in orbit, cannot resolve such an object. The diffraction limit of any single mirror, the fundamental rule that determines how sharply that mirror can see, would smear the star out into a blob. You would learn nothing about its actual size. To resolve a star at that distance, you need a different kind of instrument entirely. You need interferometry. Interferometry is one of the most elegant ideas in modern astronomy. Instead of using a single large telescope, you use multiple smaller telescopes, separated by large distances, and you combine their light in a very precise way. The effective resolution of the resulting image is not determined by the size of each individual telescope, but by the distance between them. If your telescopes are spaced 100 meters apart, you effectively have the resolving power of a telescope 100 meters across. This does not mean you have the light-collecting power of such a telescope. You still only gather as much light as your actual mirrors can collect. But for the purpose of seeing fine detail, of resolving small angles, of distinguishing two nearby points from one another, you suddenly have access to resolution that no single telescope on Earth could ever achieve on its own. The Very Large Telescope Interferometer, located in the Atacama Desert of northern Chile, is one of the most sophisticated interferometric arrays ever built. It combines the light from four main telescopes, each 8 meters across, with additional smaller auxiliary telescopes. The light from all of these instruments is brought together in an underground tunnel system where it is combined with extraordinary precision. The path lengths must be matched to within fractions of a wavelength of light. Air currents, vibrations, even the slow expansion and contraction of the ground due to temperature changes, all of it must be compensated for. It is one of the most demanding engineering feats in modern science, and it is the instrument that finally allowed astronomers to do something nobody had ever done before. It allowed them to take an image, an actual resolved image, of a star outside our own galaxy. That star was WOHG 64. The observations were carried out over several years, with the data carefully analyzed and reanalyzed, and the result, when it was finally released, stunned the astronomical community. For the first time in history, we were looking at a star in another galaxy as something more than a point of light. We were seeing it as an object, a disk, a structure, a world. The image was not crisp. It was not what you might call beautiful in the way that a Hubble image of a nebula is beautiful. It was fuzzy, blocky, low resolution. But it was real. It showed the star surrounded by an extended, egg-shaped cocoon of dust. A cocoon that the star itself had created by shedding its outer layers over thousands of years. The dust was glowing faintly in infrared, heated by the star at its center. And the star itself, deep within that cocoon, was clearly enormous. The estimates that emerged from these observations placed WOH G64's radius at somewhere between 1,500 and 2,000 times that of the Sun. Some analyses pushed it even higher. The exact number depends on assumptions about the geometry of the dust shell, the precise distance to the Large Magellanic Cloud, and a number of other factors that introduce uncertainty into the final calculation. But even at the conservative end of the range, this is a star in the same league as Stephenson 218, UY Scuti, and the other titans we previously thought we had catalogued at the very limits of stellar physics. At the upper end of the range, it might be larger than any of them, and it sits in another galaxy. Think about that for a moment. We have spent decades cataloguing the largest stars in our own Milky Way, combing through dust clouds, parsing infrared signatures, refining distance estimates, working our way through tens of billions of stars to identify the few dozen or so that qualify as true hypergiants. And now, when we point our most advanced instruments at a satellite galaxy nearly 200,000 light-years away, the very first star we manage to actually resolve turns out to be at the upper limit of what we have ever measured. The implications are staggering. If the first one we resolve is this big, how many more are hiding there? How many more are hiding in galaxies further out, beyond our current reach? Are we systematically undercounting the largest stars in the universe simply because we have not been able to see them clearly until now? This is the question that has lit a quiet fire under the astronomical community. Because if WOH G64 is a candidate for the largest known star, and if other similar objects are likely to exist in nearby galaxies, then our understanding of the upper mass limit and the upper size limit of stars may need to be revised. The textbooks may need updating. The models may need refining. The basic question of how big a star can get, which most astronomers had quietly considered more or less settled, is suddenly wide open again. But the size of WOH G64 is only part of what makes it remarkable. The other part, the part that gives the observations their character of urgency, is what is happening to the star right now. Because WOH G64 is not stable. It is not sitting placidly in the Large Magellanic Cloud, slowly burning through its fuel like our sun. It is in crisis. It is shedding mass at a furious rate. The dust cocoon that the Very Large Telescope Interferometer imaged is not some ancient feature. It is recent. It is ongoing. The star is, in real time, throwing off its outer layers into space, and the structure of that ejected material tells us that something dramatic is happening to it. Some astronomers believe the star may be in the final stages of its life. Some suggest it could explode as a supernova within a relatively short cosmic timescale. Others are more cautious, arguing that we are seeing a phase of intense instability that may last considerably longer before the final collapse comes. What is clear is that the star has dimmed significantly in recent years. Earlier observations, from the 1980s and 1990s, showed it considerably brighter than it is today. Something has changed. Dust has built up around it, blocking some of its light. The star has shed material in episodic bursts. The cocoon we are seeing is not a smooth, even shell. It is asymmetric. It is egg-shaped. It suggests that the mass loss has not been uniform. The star is throwing material off in particular directions, perhaps because of rapid rotation, perhaps because of a companion star pulling at it from some angle, perhaps for reasons we have not yet fully understood. Whatever the cause, the result is a star that is visibly changing on human timescales. A star whose evolution is happening fast enough that we can watch it unfold over decades. That by itself is rare. Most stars change so slowly that nothing detectable happens in a human lifetime. Even hypergiants typically evolve on timescales of thousands or millions of years. But WOH G64 is doing something unusual. Whether that something culminates in supernova next year or next century, we cannot say. But the fact that we are able to ask the question, the fact that this star has become an object of active monitoring rather than a static entry in a catalogue, is a sign of how much the field has changed. To understand why WOH G64 has become such an extraordinary case, we need to step back and look at how it was discovered in the first place. The story begins in the late 1970s and early 1980s, when three Swedish and Danish astronomers, Bengt Westerlund, Anders Olander, and Bertil Hedin, were conducting a systematic survey of the large Magellanic Cloud. Their goal was to identify cool, luminous stars within that satellite galaxy. Specifically, they were hunting for the carbon stars and red supergiants that tend to populate the late stages of stellar evolution. These objects are scientifically valuable because they trace the chemical history of the galaxy they inhabit. They're also relatively easy to spot, if you know what to look for, because their distinctive red color and strong infrared emission make them stand out against the bluer background of younger, hotter stars. The large Magellanic Cloud is an ideal hunting ground for such objects. It is close enough that individual bright stars can be detected and catalogued. It contains a rich variety of stellar types, and crucially, it sits at a known and relatively well-determined distance, meaning that once you know how bright a star appears, you can convert that into a precise measurement of its actual luminosity. In our own galaxy, distance measurements to individual stars can be tricky and uncertain. In the large Magellanic Cloud, you can assume that all the stars are at roughly the same distance, and that simplifies the math considerably. When Westerlund, Olander, and Hedin compiled their catalogue, WOHG64 was simply one entry among many. They noted that it was unusually red, unusually bright in infrared, and likely to be a late-type supergiant of some kind. But they did not flag it as exceptional. In the context of their survey, it was just one more interesting object. The catalogue was published, the data was archived, and astronomers moved on to other projects. WOH G64 sat quietly in the literature for years, occasionally mentioned in papers about red supergiants in the Magellanic Clouds, but never the subject of intense scrutiny. That began to change in the 1980s and 1990s as infrared astronomy matured. The Infrared Astronomical Satellite, launched in 1983, mapped the entire sky in infrared wavelengths and detected enormous amounts of dust-rich, infrared bright sources. WOH G64 turned out to be one of the brightest infrared sources in the large Magellanic Cloud. That was significant. It meant the star was either incredibly luminous or surrounded by an unusually thick shell of warm dust, or both. Follow-up observations from the ground confirmed that WOH G64 was extraordinarily bright in the infrared, far brighter than a typical red supergiant would be. Something was different about this star. It was emitting most of its energy not as visible light, but as heat in a way that suggested it was deeply embedded in a cocoon of its own making. By the 1990s, astronomers had begun to suspect that WOH G64 was not just a red supergiant. It might be something more extreme, a red hypergiant. The distinction matters. A red supergiant is already a remarkable object, a massive star in the late stages of its evolution, swollen to hundreds of times the sun's radius. A red hypergiant is a step beyond that. It is a star that has pushed even further, expanded even more, and is on the verge of catastrophic instability. The boundary between supergiant and hypergiant is not perfectly defined, but it is generally drawn at the point where a star's luminosity begins to approach the so-called Eddington limit, the theoretical maximum brightness beyond which radiation pressure exceeds gravity, and the star starts to blow itself apart. WOHG 64 sat near that limit. Its inferred luminosity, based on early estimates, was somewhere around 500,000 times that of the Sun. That placed it firmly in hypergiant territory. But the exact numbers were uncertain because the dust surrounding the star absorbed and re-emitted a significant fraction of its light. To get a clear picture of the underlying star, astronomers needed to look through the dust. And the only way to do that was with infrared instruments, ideally with spectroscopy, which could analyze not just the brightness, but the detailed chemical composition of the light coming from the star and its surroundings. In the early 2000s, observations using the Very Large Telescope's mid-infrared instruments began to reveal the structure of WOHG 64's environment in greater detail. Astronomers detected silicate dust, water vapor, and other molecules consistent with a cool, mass-losing red hypergiant. The geometry of the dust shell appeared to be elongated, not spherical. This was an early hint that the mass loss was not symmetric. Something about the way the star was throwing off material suggested a complex underlying mechanism, possibly involving rapid rotation or interaction with an unseen companion. Then, in the 2000s and 2010s, a series of observations with increasingly sophisticated instruments began to refine the picture further. Spectroscopic studies revealed that WOHG 64 was indeed losing mass at an enormous rate. Estimates suggested the star was shedding the equivalent of roughly 1,000th of a solar mass every year. To put that in perspective, our Sun loses about 1 trillionth of its mass per year to the solar wind. WOHG 64 was losing mass roughly 1 billion times faster. Over the span of 1 million years, it could shed enough material to equal the entire mass of our Sun many times over. This mass loss was building up the thick dust cocoon that infrared observations had been detecting. The cocoon was, in essence, the star's own outer layers, expelled into space, cooling, condensing into dust grains, and forming a thick veil around the underlying star. From Earth, we could see the cocoon glowing brightly in infrared because the dust was being heated by the star within. But the star itself remained largely hidden from direct view in visible light. It was as if WOHG 64 was wrapping itself in its own funeral shroud, preparing for an end that astronomers could sense approaching, but could not precisely time. The dimming that occurred between earlier observations and more recent ones was particularly intriguing. In the 1980s, WOHG 64 had been brighter in the optical wavelengths. By the 2010s, it had faded substantially. Some of this could be attributed to the buildup of additional dust between us and the star, blocking some of its visible light. Some of it might also reflect actual changes in the star itself, perhaps a contraction phase following an earlier expansion or a shift in the spectral energy distribution as the star evolved. Either way, the dimming was a sign that this was not a static object. WOHG 64 was actively changing, and we were watching it change in real time. This is what eventually led to the most dramatic chapter in the star's observational history. In the early 2020s, a team of astronomers led by Kiichi Onaka of the Universidad Andrés Bello in Chile decided to attempt something that had never been done before. They wanted to use the Very Large Telescope Interferometer's most advanced instrument, an upgrade called gravity, to actually resolve the surface of WOHG 64. To produce, in other words, the first ever direct image of a star in another galaxy. The technical challenge was enormous. Gravity operates in the near-infrared, combining light from multiple telescopes with extraordinary precision. To resolve a star as far away as WOHG 64, the instrument has to detect angular sizes on the order of less than a milliarc second. That is roughly equivalent to trying to make out a soccer ball on the surface of the moon from your backyard. It pushes the limits of what is physically achievable, given the diffraction limits of light and the precision of modern instruments. But the team was confident that gravity had the capability, and WOH-G64 was the ideal target. It was bright enough in infrared to provide a strong signal, large enough in angular size to be theoretically resolvable, and interesting enough scientifically to justify the considerable observational effort. The observations were carried out over a period of several years. Multiple nights of data collection, careful calibration, and extensive post-processing were required to produce the final result. When the image emerged, it was, by the standards of high-resolution astronomy, modest. A blurry, low-resolution glimpse of a stellar disk surrounded by an asymmetric envelope of dust. But by the standards of what had ever been achieved before, it was revolutionary. For the first time, humanity was looking at a star in another galaxy not as a point of light, but as an actual object with measurable structure. The image showed WOH-G64, surrounded by an elongated, egg-shaped cocoon of dust. The cocoon was not centered on the star. It was offset, distorted, asymmetric. This suggested that the mass loss was not happening uniformly in all directions. Material was being thrown off preferentially along certain axes. The cause of this asymmetry remained somewhat unclear, but several possibilities were proposed. One was that WOH-G64 might have a companion star, a second object orbiting close to it, whose gravitational influence was shaping the outflow of material. Another was that the star itself was rotating rapidly enough to flatten the mass loss into a disk-like geometry. A third possibility was that the star was experiencing some form of localized eruption, a violent ejection of material from one region of its surface that had skewed the overall structure of the cocoon. Whatever the cause, the implications were profound. WOH-G64 was not just a star, it was a system in transition. A massive object undergoing rapid, observable change, with structure that hinted at processes we did not fully understand. And its size, based on the new measurements, was at the upper end of what had been estimated before. Some calculations suggested a radius of roughly 1,500 solar radii, others pushed it higher. The exact number remained dependent on the assumed distance and the precise modeling of the dust shell, but the consensus was clear. This was one of the largest stars ever directly observed, and it was the first one whose surface had ever been imaged outside our own galaxy. The discovery prompted an immediate flurry of follow-up work. If WOH-G64 was this large, and if it was undergoing such dramatic changes, then it became an object of paramount importance for understanding the end stages of massive stellar evolution. It also raised the question of what other similar objects might be lurking elsewhere in the Large Magellanic Cloud, or in the Small Magellanic Cloud, or in even more distant galaxies, waiting for the next generation of instruments to reveal them. The implication was that we had probably been undercounting the population of extreme stars in nearby galaxies for decades, simply because our instruments had not been good enough to detect them clearly. Now, with gravity and similar interferometric tools, that situation was beginning to change. Once you have a measurement, the next question is always what to do with it. What does a radius of 1,500 or 2,000 solar radii actually mean? How do you take that number and make it real? Because in astronomy, the temptation is always to keep things abstract, to use scientific notation, to round to convenient powers of 10, to express enormous quantities in shorthand that obscures their physical reality. A star with a radius of 1,500 times the sun's radius sounds large. It even sounds impressive. But until you sit with that number for a while, until you try to picture it, it remains an abstraction. So let us try to make it concrete. The sun's radius is approximately 432,000 miles. That is the distance from the sun's center to its visible surface, the layer we call the photosphere. Multiply that by 1,500 and you get 648 million miles. That is the radius of WOH-G64 if the lower end of current estimates is correct. The diameter, the distance straight across the star from one side to the other, is twice that, or about 1.3 billion miles. If the upper end of the estimates is correct, with a radius closer to 2,000 solar radii, then the diameter approaches 1.7 billion miles or more. These numbers are difficult to grasp because nothing in our daily experience prepares us for them. The Earth is about 8,000 miles in diameter. The Sun is about 865,000 miles in diameter, roughly 100 times the diameter of the Earth. WOHG-64, at the upper end of its estimated size, would have a diameter approaching 2,000 times that of the Sun, or 200,000 times the diameter of the Earth. The numbers spiral outward into territory where intuition simply fails. So let us try another approach. Let us walk through what would happen if you took our solar system, removed the Sun, and placed WOHG-64 at its center. Earth's orbital distance from the Sun is roughly 93 million miles. The distance we call 1 astronomical unit. The radius of WOHG-64, even at the conservative end of estimates, is about 648 million miles. That works out to roughly 7 astronomical units, 7 times the distance from the Earth to the Sun. The surface of this star, the layer where its atmosphere transitions from opaque to transparent, would sit out around the orbit of Jupiter, which orbits at roughly 5.2 astronomical units. Jupiter would be inside the star, not near it. Not approaching it, inside it. But the conservative estimate is just the lower bound. At the upper end of current estimates, with a radius approaching 2,000 solar radii, or about 860 million miles, the surface of WOHG-64 would extend out to roughly 9.5 astronomical units. That is essentially the orbital distance of Saturn. The ringed planet, that distant marvel that takes nearly 30 years to complete one orbit of our Sun, would find itself sitting right at or just inside the star's outer surface. The rings would be obliterated long before they reached that distance, vaporized by the intense radiation and the searing heat of the stellar envelope. Saturn itself would be deep within the star's atmosphere, surrounded on all sides by glowing hydrogen plasma at temperatures hot enough to vaporize any solid matter. Take a moment to let that sink in. You have probably seen images of Saturn, photographed by spacecraft like Voyager and Cassini. You have seen its golden bands of cloud, its delicate ring system, its strange hexagonal storm at the North Pole. All of that, every detail, every feature would be gone, crushed, vaporized, engulfed, reduced to its constituent atoms and dispersed into the outer layers of a single star. The orbit that takes Saturn nearly 3 decades to complete, sweeping out a path through the solar system roughly 6 billion miles in circumference, would lie entirely within this one stellar body. Everything closer to the Sun, Mercury, Venus, Earth, the Moon, Mars, the entire asteroid belt, Jupiter and all its moons, would also be inside the star. Only Uranus and Neptune, orbiting at 19 and 30 astronomical units respectively, would remain outside, swept by the star's enormous stellar wind, surrounded by its radiation, but at least technically beyond its surface. This is the scale of what we are dealing with. A star so large that nearly the entire region of space we call the solar system would fit inside it, with room to spare. And yet, despite this almost incomprehensible size, WOHG-64 is not particularly massive. Current estimates place its mass at roughly 20 to 40 times that of the Sun. That is significant, certainly. The Sun is already an enormous object by any human standard, and a star 40 times its mass contains enough material to make tens of millions of Earths. But it is not anywhere close to 40 times the volume of the Sun. The volume of WOHG-64, given its radius, is on the order of 1 billion to 10 billion times the volume of the Sun. The mass is at most 40 times the Sun's mass. Divide one by the other, and you get an average density that is almost unbelievable in its tenuousness. If you took a cubic meter of WOHG-64's outer atmosphere and weighed it, you would find that it contained a tiny fraction of a gram of material. Less than the weight of a grain of sand. Less, in many cases, than the air in your living room. The outer envelope of this star is, by any reasonable standard, a vacuum. A glowing, blazing, multi-thousand-degree vacuum, but a vacuum nonetheless. The atoms are spread so thinly through that enormous volume that the average density rivals that of laboratory vacuums on Earth. This is a strange thing to contemplate. We tend to imagine stars as solid, glowing balls of fire. We picture them as something like the sun, with a defined surface and a churning interior. But hypergiants are not really solid in any meaningful sense. They do not have surfaces in the way the Earth has a surface, or even the way the sun does. The transition from inside the star to outside the star is gradual, not sharp. As you move outward from the core, the density drops continuously. There is no clear line where the star ends and space begins. The photosphere, the layer we call the surface, is just the depth at which the gas becomes transparent enough that we can see through it. It is a visual boundary, not a physical one. In the case of WOH G64, the photosphere sits somewhere out around the equivalent of Saturn's orbit. But beyond that, the atmosphere does not simply stop. It continues outward, becoming progressively more tenuous, blending eventually into the dust cocoon that surrounds the star, and from there into the surrounding interstellar medium. The star, in a real sense, has no clear edge. It fades into space. The dust shell that the gravity observations imaged, that elongated egg-shaped cocoon, is essentially WOH G64's extended atmosphere, the part of the star that has been thrown outward and is now drifting away into the large Magellanic Cloud. Inside the star, however, the picture is very different. As you move from the diffuse outer envelope inward toward the core, the density rises continuously. Temperatures climb. Pressures multiply. The behavior of matter changes dramatically. In the deepest layers, where nuclear fusion is taking place, conditions become extreme beyond anything that exists naturally on Earth. The core temperature of a hypergiant, like WOH G64, likely exceeds 200 million degrees Kelvin in its current evolutionary phase, possibly much higher depending on what nuclear burning stage it has reached. The density there is comparable to or higher than that of the densest metals we know. In that core, matter is not gas in any familiar sense. It is plasma at conditions where atoms cannot exist intact. Electrons are stripped from their nuclei. Bare atomic nuclei collide with one another at speeds high enough to overcome their mutual electrical repulsion and fuse into heavier elements. Energy pours out of these reactions at rates that would vaporize any solid material that came near. This is the engine of the star, the source of its enormous luminosity, the reason it shines. The energy generated in the core takes an enormous amount of time to work its way out to the surface. In the Sun, the typical photon released by core fusion takes something like 100,000 years to random walk its way through the radiative zone to the convection zone, and then another few months to reach the surface. In a hypergiant like WOH G64, the structure is somewhat different, but the basic principle holds. Energy generated in the core is slowly transporting outward through layers upon layers of plasma, eventually reaching the convective envelope, where it is carried the rest of the way by giant rising columns of hot gas. By the time it reaches the photosphere and escapes as light, that energy has been on a journey of many thousands of years from where it was first produced. This means, in a curious way, that when we look at WOH G64, we are seeing energy that was generated in the star's core long ago. Not just the 160,000 years it took the light to travel from the large Magellanic Cloud to our telescopes, but additional millennia or tens of millennia spent diffusing outward through the star's interior. The light we see tonight is, in a sense, ancient even by the standards of the star itself. It tells us about conditions inside the star at a time long before the photons ever reached the surface. If something had changed inside the core in the past few hundred years, we would not yet see the consequences in the surface light. The star would have to wait for those changes to propagate outward before we could detect them. This is the strangeness of trying to study an object so large and so distant. You are never seeing it in real time. You are seeing layered echoes of its past, with different layers corresponding to different timescales, all overlapping in the light that finally reaches your telescope. To really appreciate what WOH G64 represents, we need to understand the broader context of how stars of this kind come to exist in the first place. Hypergiants are not born as hypergiants. No star emerges from a collapsing cloud of gas already 1,500 times the radius of the Sun. The size, the redness, the swollen instability, all of it is the product of evolution. A long sequence of changes that begins with a much more compact, much hotter, much different kind of star and ends, eventually, in the kind of bloated cosmic giant we are observing today. To trace that path, we have to go back to the formation of WOH G64 itself, somewhere between 5 and 10 million years ago. Astronomers cannot date massive stars with the same precision they can use for our Sun, because hypergiants do not stay around long enough to accumulate the kind of evidence we have for older, calmer stars. But we know enough about how stars form and how they evolve through their lifetimes to reconstruct the general outline of WOH G64's biography. In its earliest days, this star did not exist as a star at all. It was part of a much larger cloud of cold gas and dust, drifting through one of the star-forming regions of the Large Magellanic Cloud. These regions, scattered throughout that satellite galaxy, are filled with the raw material of star formation: hydrogen, helium, and trace amounts of heavier elements, organized into vast clouds that can stretch across hundreds of light years. The clouds are mostly cold and quiet, with temperatures only slightly above absolute zero in their interiors. But they are not static. Turbulence, shock waves from nearby supernovae, the gravitational pull of passing stars, and the slow, inexorable force of self-gravity all act on the gas. Over time, denser regions begin to collapse. When a particular pocket of gas becomes dense enough that its own gravity exceeds the outward pressure of its thermal motion and turbulence, collapse becomes inevitable. The cloud begins to fall in on itself. As it falls, it heats up, both because gravitational energy is being converted into thermal energy, and because the increasing density makes it harder for radiation to escape. At the center of the collapsing cloud, conditions rapidly approach those needed for nuclear fusion. Once the core temperature reaches roughly 10 million degrees Kelvin, hydrogen begins fusing into helium, and a star is born. In the case of WOH G64, the initial mass of the collapsing cloud must have been enormous. To eventually evolve into a hypergiant, the progenitor star needed to start its life with at least 25 to 40 times the mass of our Sun, possibly more. These are stars at the upper end of the mass range that nature can produce. They are rare, they are violent, and they are short-lived. The relationship between a star's mass and its lifespan is roughly inverse and steeply nonlinear. A star like the Sun burns through its hydrogen fuel over the course of roughly 10 billion years. A star 10 times the Sun's mass burns through its fuel in only about 20 million years. A star 40 times the Sun's mass might exhaust its core hydrogen in just 4 or 5 million years. This is because massive stars are spendthrifts. They burn hot, they burn bright, and they burn fast. The pressure in their cores is enormous, the temperatures are extreme, and the rate of fusion scales steeply with these conditions. A massive star can produce 100,000 or even 1 million times more energy per second than the Sun, but it does so by consuming its fuel at correspondingly higher rates. The result is a brief, brilliant existence, ended by collapse and explosion. When WOH G64 was first born, it was nothing like the red hypergiant we see today. It was a blue main sequence star, hot, dense, and compact. Its surface temperature probably exceeded 30,000 degrees Kelvin, which would have made it appear bluish-white to the eye. Its radius would have been only 10 or 20 times that of the Sun, large by stellar standards, but tiny compared to its current size. Its luminosity would already have been enormous, perhaps hundreds of thousands of times that of the Sun, but most of that energy would have been emitted in ultraviolet wavelengths, invisible to the human eye. For the first few million years of its life, WOH G64 sat on the main sequence, steadily fusing hydrogen into helium in its core. The star was stable in the same general sense that any main sequence star is stable. The outward pressure of fusion-generated radiation balanced the inward pull of gravity, and the star maintained a roughly constant size and luminosity over that period. But the stability was always temporary. The star was steadily depleting its core hydrogen, converting it into helium ash that accumulated at the center. With each passing million years, the fuel reserves dwindled. When the core hydrogen finally ran out, everything began to change. Without the energy from fusion to support it, the core began to contract under its own gravity. As it contracted, it heated up. The temperature in the core climbed past the threshold needed to fuse helium into carbon, and a new round of fusion began. Helium burning is a more energetic process than hydrogen burning, producing less energy per reaction, but proceeding at higher temperatures and with different rates. As the core compressed and heated, the outer envelope of the star responded by expanding. This expansion is one of the most dramatic events in a star's life. The same star that had been a compact blue object for millions of years suddenly began to swell outward. Its outer layers, no longer compressed by the same conditions that had governed them on the main sequence, began to spread out into space. As they spread out, they cooled. The surface temperature of the star, which had been over 30,000 degrees Kelvin, dropped dramatically. As the temperature dropped, the color of the star shifted. It went from blue to white to yellow to orange to red. By the time the expansion was well underway, WOH G64 had become a red supergiant, possibly with a radius of several hundred times that of the Sun. But the evolution did not stop there. As helium burning continued in the core, and as additional fusion shells ignited around the core in onion-like layers, the star continued to expand. Carbon burning began, then neon burning, then oxygen burning. Each new stage of fusion happened at progressively higher temperatures, proceeded at progressively higher rates, and lasted for progressively shorter times. By the time WOH G64 reached its current state as a red hypergiant, it had likely passed through multiple stages of nuclear burning and was either in the late stages of helium burning or possibly even further along the chain. Each transition was accompanied by additional expansion and cooling of the envelope. The star grew larger and larger. Its outer layers became more diffuse, more turbulent, more loosely bound. The luminosity remained enormous, but the surface temperature continued to drop. By the time we observe WOH G64 today, its surface temperature is probably around 3,400 degrees Kelvin. That sounds hot by everyday standards, and it is. It is far hotter than any flame you could light on Earth. But by stellar standards, it is cool. It is the temperature characteristic of a red supergiant or hypergiant, a star in the late stages of its evolution. This is a critical point to understand about WOH G64. It is not a young, vigorous star burning brightly in the prime of its life. It is an old star in stellar terms, even though its total age might only be a few million years by human reckoning. It has burned through most of its nuclear fuel. The remaining material in its core is increasingly heavy, increasingly stable against fusion, and increasingly difficult to extract energy from. The star is, in essence, running out of options. Eventually, this process leads to a crisis. Once the core has fused its way up the periodic table to iron, fusion can no longer release energy. Iron is the most tightly bound nucleus, and fusing it into heavier elements actually consumes energy rather than producing it. When the core becomes mostly iron, fusion stops. The outward pressure that has supported the star against gravity disappears. The core collapses catastrophically in a fraction of a second, and the rest of the star follows it inward, only to rebound off the now incompressible neutron-rich core in a violent explosion. This is the core collapse supernova, the dramatic and luminous death of a massive star. WOH G64 is approaching this end. We do not know exactly how close it is to the final explosion. The visible signs, the dimming, the dust shell, the asymmetric mass loss, all suggest a star in distress, but stars in this phase can linger for tens of thousands of years before the final collapse, or they can erupt in spectacular ways much sooner. There is no precise way to predict the timing from the outside. What we can say is that the explosion is inevitable. It is built into the physics. When WOH G64 finally dies, it will do so as a supernova, and the event will be visible from Earth as a dramatic brightening of that point of light in the large Magellanic Cloud. If the supernova happens in our lifetimes, it will be one of the most studied astronomical events in history. We have the instruments now to observe a supernova in extraordinary detail. Neutrino detectors deep underground would catch the burst of particles released by the core collapse. Gamma-ray telescopes in orbit would detect the high-energy radiation produced by the explosion. Optical and infrared telescopes around the world would track the brightening and fading of the visible event. We would learn things about supernovae and massive stellar death that we currently can only theorize about. The last supernova visible to the naked eye in or near our galaxy was supernova 1987A, which occurred in the Large Magellanic Cloud, the very same satellite galaxy where WOH G64 resides. That event, in February 1987, was the brightest supernova in nearly 400 years. It was studied intensively, and it taught astronomers an enormous amount about how massive stars die. If WOH G64 explodes, it would join the company of 1987A as another close-by supernova in our cosmic neighborhood. The data it would produce could be transformative, but the timing remains the great unknown. The explosion could happen tomorrow. It could happen in 10,000 years. From our perspective, the star is already as it appears today, with all the light reaching us delayed by 160,000 years of travel. For all we know, WOH G64 has already exploded, and the light of that supernova is currently somewhere in interstellar space, on its way to us, perhaps already past the halfway mark. We simply have no way to know until the light arrives. The dimming of WOH G64 over the past several decades has been one of the most intriguing pieces of evidence that the star is approaching a critical moment in its evolution. To appreciate the significance of this dimming, we need to put it in context. Stars are not, by nature, things that change quickly. The sun, for instance, has been remarkably stable in its brightness for the past several billion years. Its luminosity varies by a fraction of a percent over decades, driven by the 11-year solar cycle and other long-term trends, but to the naked eye it appears essentially constant from one generation to the next. This stability is the norm for stars in the prime of their lives. They burn steadily, year after year, century after century, with only the slightest variations. Massive stars in their later stages are different. They are unstable. They pulsate. They erupt. They fade and brighten on timescales that, while still long by human standards, are short enough that astronomers can actually observe the changes in real time. WOH G64 is a textbook example of this kind of late-stage instability. The observations from the 1980s and 1990s show a star noticeably brighter than what we see today. Over the course of roughly 40 years, the visible light from WOH G64 has decreased significantly. The exact magnitude of the change varies depending on the wavelength being measured and the specific epoch of observation, but the trend is clear. The star is dimming. There are several plausible explanations for this dimming, and astronomers have been debating which one or combination best fits the data. The first and most straightforward explanation is dust. As we have discussed, WOH G64 is in the process of shedding mass at an enormous rate. The material being expelled cools as it moves outward, and at sufficient distance from the star, it begins to condense into solid dust grains. Over time, this dust accumulates around the star, forming the cocoon that gravity imaged so clearly. As more dust is produced, more visible light from the star is absorbed by that dust before it can reach Earth. The dust radiates the absorbed energy in infrared wavelengths, which is why WOH G64 appears so bright in infrared while becoming dimmer in visible light. This dust buildup hypothesis explains a significant portion of the observed dimming, but dust alone may not account for everything. There is also evidence that WOH G64 itself is undergoing changes in its outer structure. The star may be contracting slightly, or its surface temperature may be shifting, or the geometry of its envelope may be evolving in ways that affect how much light reaches us. Hypergiants in the late stages of their evolution are known to undergo episodic events of dramatic mass ejection, sometimes called eruptions or outbursts. These events are not as dramatic as a supernova, but they can be substantial enough to significantly change the star's appearance over the course of years or decades. WOH G64 may be in the midst of such an outburst, or may have recently undergone one whose effects we are still observing. The most famous example of this kind of pre-supernova behavior comes from a star in our own galaxy. Eta Carinae, located about 7,500 light-years from Earth, is a luminous blue variable that underwent a massive eruption in the 1840s. During the so-called Great Eruption, Eta Carinae briefly became the second brightest star in the night sky, despite its enormous distance. The eruption ejected an enormous amount of material into space, forming what is now known as the Homunculus Nebula, a bipolar cloud of gas and dust that can be observed expanding outward from the star to this day. Eta Carinae did not explode as a supernova during that eruption. It survived, but the event was a sign that the star is in the late stages of its life, and astronomers consider it a likely candidate for a supernova explosion in the relatively near future, possibly within the next few 100,000 years. WOHG 64 may be doing something similar, though on a different scale and with a different geometry. The dust cocoon that surrounds it, the asymmetric egg shape, the ongoing mass loss, all of these are consistent with a star that is, in some sense, struggling against gravity, struggling against its own radiation pressure, struggling against the limits that nature places on how large and how luminous a star can be without tearing itself apart. That struggle, that delicate balance between forces trying to expand the star and forces trying to contract it, is at the heart of why hypergiants exist at all. Every star, throughout its life, is engaged in this balancing act. Gravity pulls inward. The pressure of hot gas pushes outward. The radiation produced by fusion adds its own outward push. Where these forces are in equilibrium, the star is stable. Where they are not, the star is changing, either growing or shrinking, gaining or losing material, evolving toward some new state. For most stars, including our Sun, the balance is comfortable. Gravity is not particularly intense in the Sun's outer layers because the Sun is not all that massive. Radiation pressure is modest because the Sun's luminosity, while enormous by human standards, is not extreme by stellar standards. The result is a stable configuration that can persist for billions of years. For hypergiants like WOHG 64, the situation is much more precarious. The mass of the star is enormous, so gravity is intense in the deep interior. The luminosity is enormous, so radiation pressure in the outer envelope is also intense. The two forces are pushing close to a critical threshold. If the outward pressure exceeds the inward pull, the star begins to lose its grip on its outer layers. Material is blown outward into space, and the star sheds mass. This is precisely what we observe in WOHG 64. The star is shedding mass continuously, and sometimes in dramatic bursts, because the balance has shifted toward instability. This brings us to one of the most important concepts in stellar physics, the Eddington luminosity. Named after the British astrophysicist Arthur Eddington, who first worked out its implications in the early 20th century, the Eddington luminosity is the maximum brightness a star can have without its radiation pressure exceeding its gravitational attraction. If a star's actual luminosity approaches the Eddington luminosity, the star begins to blow itself apart. Radiation pressure starts to drive material away from the surface faster than gravity can hold it in place. The result is intense mass loss, and ultimately the inability of the star to maintain its current structure. The Eddington luminosity scales linearly with mass. A more massive star can be more luminous without exceeding the limit, but there is an upper bound. Beyond a certain mass, even the Eddington limited luminosity cannot sustain a stable star. Theoretical calculations suggest that the upper mass limit for stars is somewhere around 150 to 300 solar masses, though there is considerable uncertainty in this number. Above that limit, the star simply cannot exist. It would blow itself apart before it could fully form. Within the limit, but still at the high end, you get stars like WOHG 64. Stars that are massive enough to push close to the Eddington threshold, and as a result, are in a state of continuous instability. The implications of this are profound. WOHG 64 is not just a large star. It is a star living at the edge of what is physically possible. Every second, the radiation pouring out from its core is pushing against the outer layers, with a force that nearly equals the gravitational pull holding those layers in place. Small fluctuations, small changes in the rate of fusion, small shifts in the opacity of the outer envelope can tip the balance one way or the other. Star can suddenly start losing more mass, or briefly become more stable, or experience eruptions that throw enormous amounts of material into space. It is, in a sense, a star perpetually on the verge of catastrophe. This is why the asymmetric dust cocoon around WOH G64 is so significant. The asymmetry tells us that the mass loss is not happening uniformly. Material is being thrown out in particular directions, in particular bursts, with particular geometries. Something is shaping the flow of material out of the star. The leading hypotheses, as mentioned earlier, include the presence of an unseen companion star whose gravity disrupts the smooth flow of mass loss, rapid rotation of the star itself, which creates an equatorial bulge and concentrates mass loss along the rotation axis, or magnetic fields that channel the outflow along particular field lines. Each of these hypotheses has implications for what will happen when WOHG64 eventually explodes. If there is a binary companion, the supernova explosion will interact with that companion in complex ways. The companion might be disrupted, even ejected from the system at high velocity. The geometry of the resulting supernova remnant will be shaped by the binary geometry. If the star is rapidly rotating, the supernova may be highly asymmetric, possibly producing a gamma-ray burst, one of the most violent kinds of explosions known in the universe. If magnetic fields play a role, the explosion may have particular polarization signatures and energy distributions that differ from a more typical supernova. We do not yet know which of these scenarios best fits WOH G64. The observations are not yet detailed enough to settle the question, but each possibility opens up an avenue for follow-up work. Each is being actively investigated by teams of astronomers using a range of instruments, and each adds to the richness of what WOH G64 represents as an astronomical target. There is another aspect to consider as well. WOH G64 is located in the Large Magellanic Cloud, which has a different chemical composition from our own Milky Way. The Magellanic Clouds are metal-poor compared to the Milky Way. They contain fewer heavy elements per unit of hydrogen and helium. This affects how stars evolve, because the abundance of heavy elements influences how stars lose mass, how their internal structures develop, and how they ultimately die. A massive star in the Magellanic Cloud may evolve somewhat differently from a similar star in the Milky Way. By studying WOH G64, astronomers are gaining insight into how stellar evolution proceeds under different metallicity conditions, which is important for understanding the universe more broadly, since most galaxies throughout cosmic history have had metallicities lower than our own. This is one of the reasons WOH G64 has become such an important object of study. It is not just remarkable in itself. It is a window into a kind of stellar evolution that is more typical of the early universe, when galaxies were younger and had not yet been enriched by generations of stars. Understanding WOH G64 helps us understand stars that lived and died long ago, in galaxies far away, in conditions we cannot directly observe. If WOH G64 is one of the largest stars we have ever directly resolved, the natural next question is whether it is alone. Whether nature, in producing this single extraordinary object, has done so as a one-time accident, or whether it has been producing similar objects routinely, and we have simply been failing to notice them. The answer, increasingly, seems to be the second. WOH G64 is not unique. It is, at most, the most prominent example of a class of stars that has been hiding from us in plain sight for decades. To understand why, we have to think about the nature of astronomical surveys and the biases built into them. When astronomers catalogue stars in nearby galaxies, they are limited by what their instruments can detect. They can see bright stars more easily than faint ones. They can see hot stars more easily than cool ones, because hot stars emit more of their energy in the wavelengths we typically observe with optical telescopes. They can see stars in regions of low dust extinction more easily than stars in regions of high extinction. All of these biases shape what we know about the stellar populations of nearby galaxies. Cool, dusty hypergiants like WOH G64 sit in the worst possible position for traditional surveys. They are cool, so they emit most of their energy in infrared wavelengths rather than visible light. They are surrounded by their own dust cocoons, which further obscure them in visible wavelengths. They are often embedded in dust-rich regions of their host galaxies, which adds additional extinction. The result is that for decades, astronomers studying nearby galaxies were essentially looking at the universe through filters that were tuned to miss objects exactly like WOH G64. The hypergiants were there. They were shining brightly in infrared. They were producing prodigious quantities of energy, but they were invisible to the surveys being conducted. This began to change with the advent of large-scale infrared surveys, starting with IRAS in the 1980s and accelerating with missions like 2MASS, Spitzer, and now JWST. As infrared catalogues improved, the population of cool, luminous, dusty stars in nearby galaxies began to come into view. WOH G64 was, in fact, one of the brightest infrared sources in the Large Magellanic Cloud, but it was only one of many such sources. The Large Magellanic Cloud contains dozens of red supergiants and hypergiants, many of which have been catalogued but not studied in detail. The Small Magellanic Cloud has its own population of similar objects. So do other nearby galaxies, including M31, the Andromeda Galaxy, and M33, the Triangulum Galaxy. The pattern that has emerged from systematic study of these galaxies is striking. Cool, luminous, dusty supergiants and hypergiants are not rare. They are a normal part of the stellar population of any galaxy that is actively forming massive stars. The rarity that astronomers had assumed for these objects was largely an artifact of detection bias, not a reflection of how often nature actually produces them. In any given galaxy, at any given time, you should expect to find a population of these extreme stars, scattered throughout the regions where massive star formation has occurred in the past few million years. This realization has important implications for our understanding of stellar evolution. If hypergiants are more common than we previously thought, then the late stages of massive stellar evolution, the phases that lead up to core-collapse supernova, are also more common than we thought. Stars are spending more time in these extreme, swollen, dust-shrouded states than older models predicted. This means that the contribution of hypergiants to the chemical enrichment of galaxies, to the production of dust in the interstellar medium, and to the overall energy budget of star-forming regions may be larger than was previously appreciated. The dust that hypergiants produce is particularly important. Dust grains in the interstellar medium are not just incidental. They are essential to the processes by which galaxies form new stars and planets. Dust grains provide surfaces on which molecules can form and accumulate. They shield the interiors of molecular clouds from harsh ultraviolet radiation, allowing those clouds to remain cold and dense enough to collapse and form new stars. They eventually become the building blocks of rocky planets. The Earth itself, every solid piece of matter you have ever touched, is descended from interstellar dust grains that were once produced by stars at the end of their lives. Hypergiants are among the most prolific dust producers in the universe. They shed enormous amounts of material, much of which condenses into dust as it cools. Understanding how much dust they produce, what kind of dust they produce, and how it is distributed in their environments is essential to understanding the broader cycle of matter in galaxies. WOH G64, with its thick, asymmetric, observable dust cocoon, is providing one of the best laboratories we have for studying this process in action. The team using gravity did not just image the star. They imaged the dust around it. They mapped the geometry, the temperature gradient, the composition. They saw with their own instruments the building blocks of future planets and future life being manufactured in real time around a dying star in another galaxy. That is worth pausing on. The dust that WOH G64 is producing today will, over millions of years, mix with the surrounding interstellar medium of the Large Magellanic Cloud. It will become part of the raw material from which new stars and new planetary systems are formed. Those new systems might one day harbor planets capable of supporting life. If they do, that life will be made in part from the atoms that WOH G64 forged in its core and ejected into space during its final phases. Stars are not just sources of light. They are factories for the chemical complexity that makes everything else in the universe possible. And hypergiants, despite their brief lives, are among the most important of those factories. But WOH G64 is not the only star pushing the limits in the Magellanic Clouds. The same surveys that revealed WOH G64 as an outstanding object have also identified other stars in the same league. Some of them may be comparable in size. Some may be even larger, though current measurements are uncertain enough that the rankings change as new data comes in. Among the notable candidates are several red supergiants in the large Magellanic Cloud that show similar signs of extreme mass loss and instability. There are also luminous blue variables, hot massive stars in unstable phases of their evolution that may be progenitors of future red hypergiants. And there are Wolf-Rayet stars, stripped-down massive stars that have lost their hydrogen envelopes entirely and are now showing their hot, helium-rich cores directly to the universe. Each of these stellar types plays a role in the late evolution of massive stars. The exact relationships between them, the sequences in which a given star might pass through these phases, and the conditions that determine which phases dominate, are still being worked out. WOH-G64 is one important data point. The other extreme stars in the Magellanic Clouds are additional data points. Together, they are building up a picture of massive stellar evolution that is far richer and more complex than the simple textbook descriptions of just a few decades ago. One particularly interesting question is whether WOH G64 might have a companion. Many massive stars are part of binary systems. They form together with one or more siblings, and they evolve in tandem, sometimes with dramatic gravitational interactions that affect their development. Binary interactions can strip a star's outer layers, accelerate its evolution, or in some cases, lead to mergers that produce even more massive stars than either component started as. If WOH G64 has a companion, the geometry of the dust cocoon we observe might be a clue to the orbit. The asymmetric, egg-shaped distribution of dust could be shaped by the gravitational pull of an orbiting companion, with material being ejected preferentially through the Lagrange points of the binary system. So far, no companion to WOH G64 has been definitively detected, but the geometry of the mass loss strongly suggests that something is shaping it. Either a companion, or rapid rotation, or magnetic fields, or some combination of these. Future observations, particularly with even higher resolution interferometry and with high-resolution spectroscopy that can detect the gravitational signature of a hidden companion, may finally settle this question. If WOH G64 does turn out to have a companion that would add another layer of complexity to its eventual death. Binary supernovae are a major area of research in modern astrophysics, in part because the resulting interactions can produce unusual outcomes. A binary companion might be ejected at high velocity by the explosion. It might be partially destroyed. In some scenarios, the supernova explosion might trigger the merger of the dying star with its companion, producing an even more spectacular outcome than a single-star supernova would. We do not yet know whether any of this applies to WOH G64, but the possibility is there, and it adds urgency to ongoing observations. The broader lesson from WOH G64 is that astronomy is still very much in the business of discovery, even in the 21st century. We sometimes imagine that the era of great astronomical discoveries belongs to the past, to Galileo, to Newton, to Hubble, to the heroic figures who first pieced together the structure of the cosmos, but the discoveries continue. They are just made with different tools, at finer levels of detail, in regions of space that previous generations could not reach. The first direct image of a star in another galaxy is a discovery that no telescope from any earlier era could have made. It required interferometric arrays that did not exist a few decades ago. It required computational techniques that were impossible before modern computers. It required a global collaboration of astronomers, engineers, and theorists working together to extract a faint but real signal from an incredibly difficult observation. And it has changed our picture of what is possible. We now know that stars in other galaxies can be resolved as objects. We now know that some of those objects are likely larger than anything we have measured in our own galaxy. We now know that the population of extreme hypergiants is broader and more diverse than we appreciated. We are at the start of a new chapter in our understanding of the largest stars, and WOHG 64 is in many ways the title of that chapter. The first object of its kind, fully resolved, fully characterized, fully recognized for what it is. A glimpse into a class of cosmic giants that we are only just beginning to map. The eventual death of WOHG 64 will be one of the most dramatic events the universe is capable of producing. We have touched on this already, but it is worth dwelling on because the supernova that ends this star's life will not be like the explosions you might see in artistic renderings or simulations. It will be something stranger, more violent, and in some sense more revealing about the nature of matter and energy than anything our minds easily picture. To grasp what is coming for WOH G64, we have to understand the mechanics of a core collapse supernova in detail, and we have to think about what makes the explosion of a hypergiant different from the explosion of a more ordinary massive star. The chain of events that leads to a supernova begins with the failure of fusion in the star's core. Throughout its life, WOH G64 has been fusing progressively heavier elements as one nuclear fuel after another is exhausted. Hydrogen to helium, helium to carbon and oxygen, carbon to neon, magnesium and sodium, neon to oxygen and magnesium, oxygen to silicon, sulfur and other intermediate mass elements, silicon to iron and nickel. Each of these stages happens at progressively higher temperatures and pressures, and each lasts for progressively shorter times. The hydrogen-burning phase of WOH G64 probably lasted around 4 or 5 million years. The helium-burning phase that followed lasted only a few 100,000 years. By the time the star reaches silicon burning, the duration is measured in days. The final stage, in which silicon is fused into iron in the core, lasts about a week. When the core becomes mostly iron, fusion stops releasing energy. Iron is the most tightly bound nucleus per nucleon, meaning that fusing iron nuclei into heavier elements actually consumes energy rather than producing it. The core, suddenly without a power source, cannot maintain the outward pressure that has been supporting it against gravity. The collapse begins. The collapse is faster than almost anything else in nature. In less than a second, the iron core, which had been about the size of the Earth, collapses to a diameter of about 20 kilometers. The density at the center reaches values comparable to that of an atomic nucleus, around 100 trillion grams per cubic centimeter. At such densities, protons and electrons are squeezed together so tightly that they merge through inverse beta decay, producing neutrons and releasing an enormous flood of neutrinos. The core becomes a protoneutron star, an object composed almost entirely of neutrons packed at nuclear density. The collapse releases an extraordinary amount of gravitational potential energy. Most of this energy, around 99% of it, is carried away by neutrinos. These ghostly particles, which interact only weakly with normal matter, pour out of the collapsing core in a flood. For a few seconds, the neutrino luminosity of a core collapse supernova exceeds the combined luminosity of every other star in the observable universe. It is, by this measure, the most powerful single event the cosmos can produce. The remaining 1% of the released energy, while tiny by comparison, is still staggering. It is enough to power the explosion that we see as a supernova, to heat the surrounding material to temperatures of billions of degrees, and to drive that material outward at velocities of thousands of kilometers per second. The mechanism by which this energy is transferred from the core to the outer layers is one of the most actively studied questions in modern astrophysics. The simple picture is that the collapsing core rebounds when it reaches nuclear density, sending a shock wave outward through the star. But detailed simulations have shown that this initial shock wave alone is not enough to drive a successful explosion. Something else has to happen. The leading explanation involves the neutrinos. As they stream outward from the collapsing core, a small fraction of them are absorbed by the material falling in toward the core. This absorption heats the material, creates pressure, and revives the stalled shock wave. The shock then propagates outward through the rest of the star, plowing through the layers of carbon, oxygen, helium, and hydrogen that make up the envelope, accelerating that material to high velocities and ultimately driving it out into space in a violent explosion. Within hours, the shock reaches the surface of the star, and the supernova becomes visible to outside observers as a sudden, dramatic brightening. For WOHG-64, this entire process will unfold in a matter of seconds inside the core and over the course of hours through the envelope. The outer layers of the star, which extend out to nearly 1 billion miles or more from the center, will be heated and accelerated and blown outward. The dust cocoon that we observe today will be vaporized by the radiation and overrun by the expanding shock wave. The material in the cocoon will mix with the material from the explosion itself, producing a complex, layered, expanding cloud that will be visible from Earth as a slowly fading bright spot in the sky. The brightness of the resulting supernova will be enormous. Type II supernovae, the kind produced by core collapse explosions of massive stars, typically reach peak luminosities of about 1 billion to 10 billion times the brightness of the Sun. They remain bright for weeks to months before fading. From a distance of 160,000 light-years, a supernova from WOH G64 will be easily visible to the naked eye, comparable in brightness to the brightest stars in the night sky, possibly even brighter. It would appear as a new star in the constellation Dorado, visible from the southern hemisphere, persisting for months before slowly dimming and eventually fading from naked eye visibility. The closest analog we have for what this might look like is supernova 1987A, which occurred in the Large Magellanic Cloud and was visible from Earth starting in February 1987. That supernova was the brightest in nearly 400 years and remained visible to the naked eye for several months. It was studied intensively by every available instrument, and it produced an enormous wealth of data that transformed our understanding of supernovae. The progenitor of 1987, A was a blue supergiant, not a red hypergiant, so the details of the explosion were somewhat different from what we would expect from WOH G64. But the general experience of observing it, the slowly evolving brightness, the spectral changes over time, the eventual revelation of the expanding remnant would likely be similar. What will be left behind after WOH G64 explodes is a question that depends on the precise mass of the iron core at the moment of collapse. If the core is below a certain threshold, the collapse halts at the neutron star stage. The resulting object is a city-sized sphere of pure neutrons, packed to nuclear density, spinning rapidly and possessing an enormous magnetic field. Such objects, when their orientation is favorable, become visible as pulsars, beaming radio waves and other radiation across the cosmos. If the iron core is above the threshold, neutron degeneracy pressure is insufficient to halt the collapse, and the core continues falling inward until it forms a black hole. In that case, the supernova explosion is still visible, but the remnant left at the center is a region of space from which no light can escape. For WOH G64, given its estimated current mass and the amount of material it has already lost, the most likely outcome is the formation of a black hole. The progenitor masses for black hole-forming supernovae are not perfectly known, but they generally lie above about 20 to 25 solar masses for stars in metal-rich environments, and somewhat higher for metal-poor environments like the Large Magellanic Cloud. WOH G64 sits in that range. The black hole that forms from its collapse will likely have a mass of perhaps 10 to 20 solar masses, depending on how much material is ejected during the explosion and how much falls back onto the central object. The formation of a black hole through core collapse is one of the most important processes in the universe. It is how most stellar mass black holes are born. These objects, scattered throughout galaxies, are the seeds from which more massive black holes grow through subsequent mergers and accretion. They are detectable through their interactions with companion stars in binary systems, where matter flowing onto the black hole heats up and emits X-rays. And dramatically, they have been detected directly through gravitational waves when pairs of them merge. The Laser Interferometer Gravitational Wave Observatory, LIGO, and its European counterpart Virgo have detected dozens of such mergers in recent years, opening up a new window onto the population of stellar mass black holes throughout the universe. If WOH G64 forms a black hole, the black hole will eventually become part of this population. It may, over billions of years, drift through the large Magellanic Cloud, occasionally encountering other stars or black holes, and ultimately, in some distant future, perhaps merging with another compact object in an event that will release gravitational waves detectable across the universe. The supernova that creates the black hole is just the first chapter of its existence. The black hole itself, once formed, can persist essentially forever, slowly evaporating through Hawking radiation over timescales so vast that they make the current age of the universe look brief. There is another possibility worth considering. If WOH G64 is rotating rapidly enough at the time of its collapse, the resulting supernova might be unusually energetic. The combination of rapid rotation and core collapse can produce what is called a collapsar, a particularly violent explosion in which jets of material are accelerated to nearly the speed of light along the rotation axis. These jets can produce gamma-ray bursts, the most energetic events in the universe outside of the Big Bang itself. A typical gamma-ray burst can release more energy in a few seconds than the Sun will produce in its entire 10 billion year lifespan. Most of this energy is concentrated into narrow beams along the rotation axis, so gamma-ray bursts are only visible from Earth if one of those beams happens to point in our direction. We do not know whether WOH G64 will produce a gamma-ray burst when it explodes. The conditions required, including sufficient rotation, sufficient mass, and the right kind of internal structure, are not certain to be met, but it is a possibility worth taking seriously. If WOH G64 does produce a gamma-ray burst aimed in our direction, the resulting flash would be detectable across the entire sky and would briefly be one of the brightest objects in our cosmic neighborhood. At 160,000 light-years, the burst would be far too distant to cause any harm to Earth. But it would be a spectacular event, and it would teach us a tremendous amount about the conditions under which gamma-ray bursts are produced. Even without a gamma-ray burst, the supernova from WOH G64 will be a defining event in modern astronomy. It will be studied by every available instrument, observed across every wavelength of the electromagnetic spectrum, and analyzed for decades after the initial explosion fades. The remnant of the explosion, the expanding cloud of material left behind, will be visible for thousands of years, slowly cooling and dispersing into the interstellar medium of the large Magellanic Cloud. The black hole, or possibly neutron star, at the center will remain as a permanent marker of where this extraordinary star once existed. When astronomers talk about the legacy of a star like WOH G64, they often focus on the supernova and the compact remnant. Those are the dramatic, visible in points. But there is another legacy, quieter and slower, that may matter even more in the long run. It is the legacy of the elements that WOH G64 will scatter across the large Magellanic Cloud when it dies. And to understand that legacy, we need to think carefully about where elements come from, what stars do with them, and why explosions like the one coming for WOH G64 are essential to the existence of everything around us, including ourselves. The universe began, roughly 13.8 billion years ago, with only the simplest ingredients. Hydrogen and helium in a ratio of about 3 to 1 by mass, with trace amounts of lithium and a handful of other light isotopes. That was it. The Big Bang produced these light elements through a brief period of nucleosynthesis in the first few minutes of cosmic history, and then the universe expanded, and cooled to a point where further fusion became impossible. For a few 100 million years after that, the cosmos contained essentially nothing but hydrogen and helium gas, slowly cooling and clumping under the influence of gravity. There were no stars, no planets, no rocky worlds, no organic chemistry. There was only gas and the dark matter that gravitationally shaped it. Everything else, every element heavier than helium, had to be made by stars. This includes carbon, the backbone of organic chemistry. It includes oxygen, which combines with hydrogen to form water and supports the respiration of nearly all complex life. It includes nitrogen, essential for proteins and DNA. It includes silicon, the dominant element in the rocky parts of terrestrial planets. It includes calcium, which makes up bones and shells. It includes iron, which makes up the cores of planets and the hemoglobin of blood. None of these elements existed in significant quantities at the start of the universe. They had to be forged, atom by atom, in the cores of stars and in the violent explosions that ended their lives. The first generation of stars, the so-called population III stars, formed from this primordial hydrogen and helium. They were probably very massive, because the absence of heavy elements meant that the gas could not cool as efficiently as gas in later generations. Cooling is essential for star formation, because gas that cannot lose heat cannot collapse to the densities needed to ignite fusion. Without the radiative cooling provided by elements like carbon and oxygen, the first stars could only form from particularly large gas clouds, and they tended to be hundreds of times more massive than the Sun. These massive population III stars lived very brief lives, perhaps only a few million years, before exploding as supernovae and seeding their surroundings with the first traces of heavy elements. Each subsequent generation of stars formed from gas that contained a slightly higher fraction of these heavier elements. The chemistry of the universe slowly enriched over billions of years, as wave after wave of stellar births, lives, and deaths recycled material from the interstellar medium back into new stars, and then back into space. By the time our solar system formed, about 4.6 billion years ago, the gas cloud from which the sun and planets emerged already contained around 2% heavy elements by mass. That 2%, small as it sounds, was enough to make all the difference. It provided the silicon, iron, magnesium, and oxygen that built the rocky planets. It provided the carbon, nitrogen, oxygen, phosphorus, and sulfur that built living things. It provided everything that makes Earth more than just a hydrogen-helium gas giant. WOH G64 sits in this long chain of stellar nucleosynthesis. It formed from gas in the large Magellanic Cloud that had already been enriched by previous generations of stars in that galaxy. Throughout its short life, it has been forging new heavy elements in its core. Hydrogen has become helium. Helium has become carbon and oxygen. Carbon has become neon and magnesium. Neon has become oxygen and silicon. Oxygen has become silicon and sulfur. Silicon, at the very end, will become iron and nickel. By the time the core finally collapses, WOH G64 will have produced enormous quantities of elements that did not exist at the start of its life. When the supernova explosion comes, it will not just release these elements, it will produce additional ones. The shock wave plowing outward through the star's envelope will heat material to billions of degrees, briefly enabling fusion reactions that could not occur during normal stellar evolution. This explosive nucleosynthesis is responsible for many of the elements heavier than iron. Gold, platinum, uranium, lead, and other heavy metals are produced in these brief moments of violence, when matter is subjected to conditions far more extreme than the cores of even the most massive stars in their normal evolution. The supernova will throw all of this enriched material into space. We are talking about perhaps 10 to 15 solar masses of gas, ejected at velocities of thousands of kilometers per second. The ejector will plow into the surrounding interstellar medium of the large Magellanic Cloud, mixing with the gas that exists there, gradually slowing down and dispersing over thousands and then millions of years. Eventually, the chemically enriched gas will become part of new clouds, new collapsing regions, new stars, new planetary systems. The atoms forged inside WOH G64 will become the atoms of future worlds. It is impossible to know what those future worlds might look like, but we can think about the timescales involved. The mixing of supernova ejecta into the interstellar medium typically takes millions of years. The formation of new stars from enriched gas takes additional millions of years. The evolution of those new stars and the formation of planets around them takes more time still. And the development of complex chemistry on those planets, if it happens at all, takes hundreds of millions or billions of years more. If any biosphere were to emerge eventually from the atoms that WOH G64 will scatter, it would not appear until vast cosmic distances of time had passed, but it would carry the legacy of this star with it. Every atom of carbon in such a future biosphere, every molecule of water, every fragment of iron in a rocky core could trace some part of its history back to the explosion of WOH G64. This is the deepest sense in which stars create the universe we live in, not just by lighting it up, but by providing the very atoms from which complexity, including life, can be built. This is also what makes WOH G64 important in a way that transcends its immediate observability. It is a participant in the ongoing process of cosmic enrichment. It is one node in a network of stellar lives and deaths that has been operating continuously for nearly 14 billion years and will continue operating for far longer. Each hypergiant that lives and dies contributes its share of heavy elements to the cosmic budget. Each one is a small but real factor in shaping what the universe will look like in the future. And there is something poetic about WOH G64's role in this. The star is, at this very moment, in the late stages of its life. It is shedding mass continuously, throwing material outward in an asymmetric, gradually expanding cocoon. It is preparing for its final eruption, though the precise timing remains unknown. In a real sense, the legacy of this star is already being deposited into the surrounding space. Even before the supernova explosion, WOH G64 has been enriching its environment with heavy elements through its stellar winds. The dust cocoon we observe is not just an obstacle to direct imaging. It is the early stage of WOH G64's contribution to the chemical evolution of the Large Magellanic Cloud. When the supernova finally happens, the rate of enrichment will accelerate dramatically. In a single explosion lasting seconds to minutes, more heavy elements will be released than the star has produced through stellar winds over its entire prior lifetime. The explosion will mix that material with the surrounding ejecta, with the dust cocoon, and with the broader interstellar medium. The Large Magellanic Cloud will be measurably more enriched after WOH G64's death than it was before, not by a huge amount, but by a real one. And those enrichments will compound over time as other massive stars in the galaxy follow similar paths. There is one more dimension to consider, and that is the role of WOH G64 in our developing understanding of cosmic history. The Large Magellanic Cloud has a lower overall metallicity than the Milky Way. This means that its stars, on average, contain fewer heavy elements than stars in our own galaxy. Studying massive stars in the Magellanic Clouds gives us a window into conditions that were more typical of galaxies in the earlier universe, before they had been enriched by as many generations of stars as our own Milky Way has been. What we learn from WOH G64 about how massive stars evolve, how they lose mass, how they die, and how they contribute to galactic chemical evolution is directly applicable to understanding the population of massive stars that existed in galaxies billions of years ago. Those ancient stars were the engines that produced most of the heavy elements that now exist in the universe. We cannot observe them directly because their light reaches us with such great redshift and such great dimness that detailed study is impossible. But by observing analogous stars in nearby low metallicity environments, we can learn what they were probably like. This is one of the underappreciated values of nearby satellite galaxies for astrophysics. They are local laboratories that approximate, in important ways, the conditions of the early universe. The Large Magellanic Cloud, the Small Magellanic Cloud, and other dwarf galaxies in our cosmic neighborhood are not exact replicas of the high redshift universe. but they are close enough that careful study yields useful insights. WOHG64, with its unique combination of extreme size, active mass loss, and impending death, is one of the most valuable single objects in this kind of comparative cosmic chemistry. Whatever future generations of astronomers eventually conclude about the precise mechanisms of massive stellar evolution at low metallicity, WOHG64 will be part of the foundation on which those conclusions rest. The data we are collecting today, the images we are now able to produce, the spectra we are now able to analyze, all of it will be cited and re-examined for decades to come. The first directly imaged star in another galaxy is a landmark observation, and the star itself, with its unusual properties and active evolution, is a landmark object. We have traveled a long way tonight. We began with a question about whether nature could really produce a star large enough to swallow Saturn's orbit, and we end with the answer not just confirmed, but multiplied. WOHG64 is not the only star of its kind. It is the first one we have managed to actually photograph as more than a point of light in another galaxy, but it is almost certainly one of many such giants scattered throughout the local group and beyond. The image of WOH G64, blurry and modest as it is, represents a turning point. It is the moment when we stopped guessing at the surfaces of stars in other galaxies and started seeing them, however faintly, as the immense and complex objects they actually are. That single observation has consequences that ripple outward through almost every part of stellar astrophysics. It tells us that the largest stars in the universe may be even larger than we thought. It tells us that they are more common than detection biases had suggested. It tells us that the late stages of massive stellar evolution are richer, more dynamic, and more important to galactic chemistry than older models implied. And it tells us that the upper limits we have placed on stellar size, mass, and luminosity may need to be revisited as our instruments continue to improve. Every assumption built into stellar physics is up for renegotiation when a single new observation pushes the known parameters beyond their previous bounds. WOHG64 has done exactly that, but the importance of WOHG64 is not only scientific. It is also, in some quieter sense, philosophical. To look at the image produced by the gravity instrument and to know that you are seeing a star in another galaxy as an actual object is to experience something that no one in any previous generation could have experienced. For thousands of years, stars were lights, pinpricks, points without dimension. Even after telescopes revealed that they were suns like ours, they remained, observationally, dimensionless. They had implied sizes, calculated sizes, inferred sizes, but not measured shapes, not images, not surfaces. They were points of light arranged on a celestial sphere, and that was the limit of what our eyes and instruments could reveal about them. Now, with one observation, that has changed. We have crossed a threshold. We have started to see stars in other galaxies the way we have for centuries seen the planets in our own solar system, as objects with structure, with surfaces, with phenomena that can be mapped and studied. The resolution is still poor compared to what we can achieve for nearby stars and planets. The images are still rough, still pixelated, still requiring interpretation. But the principle is established. The next generation of instruments will sharpen what we can see. The generation after that will sharpen it further. Within a few decades, we may have detailed images of dozens or hundreds of stars in nearby galaxies, with surface features, rotation patterns, and time-variable phenomena all mapped in detail. This is the trajectory of astronomy. Each generation builds on the last. Each new instrument reveals what was previously hidden. Each new observation opens up new questions that the previous generation could not have asked. WOHG64 is, in this sense, both a milestone and a starting point. It is a milestone because it is the first star outside our galaxy whose surface has been resolved. It is a starting point because the techniques that produced its image will be applied to many more stars in the years to come, and each new resolved star will teach us something we did not know before. There is one more thought to leave you with. When you look up at the night sky from the southern hemisphere on a clear evening, you can sometimes see the large Magellanic Cloud as a faint smudge of light in the constellation Dorado. It looks like a small detached piece of the Milky Way, hanging off to one side. To the unaided eye, it is just a soft glow. It contains roughly 30 billion stars, but at a distance of 160,000 light-years, those stars blur together into a single luminous patch. You cannot pick out individual stars within it without optical aid. You certainly cannot see WOHG64 directly. It is invisible to the naked eye, buried in dust, lost in the background glow of its host galaxy. But it is there. Right now, somewhere in that faint southern smudge, this colossal star is burning. It is shedding mass into space at rates that defy intuition. It is wrapped in a dust cocoon that distorts and reshapes its light. It is approaching, however slowly, the end of its existence. The light reaching us tonight from WOH G64 left the star around 160,000 years ago. At that time, the early ancestors of modern humans were just beginning to spread across Africa. Anatomically, modern humans had emerged. Stone tools were being refined. Fire was being mastered. The first hints of symbolic thought, of language, of culture, were beginning to emerge in our species. The light that is arriving at our telescopes tonight set out on its long journey before any human had drawn on a cave wall, before any human had crossed into Europe or Asia, before any human had imagined the existence of stars as distant suns. And the star is still going, or was, when that light left. We cannot know what condition WOH G64 is in right now, because we cannot see right now. We can only see 160,000 years ago. The star could have already exploded. The light from that explosion could be in transit, racing toward us across the gulf of intergalactic space, perhaps already past the halfway mark of its journey. Or the star could still be there, still slowly evolving, still shedding mass, with the explosion yet to come. We will not know until the news arrives, in whatever form, carried by photons that left the star at whatever moment they were emitted. This is the peculiar relationship that astronomy creates between observer and observed. We are connected to objects vastly removed from us in space and time, but only across a delay that nothing can shorten. The information we receive is always old. The universe we see is always a memory. And yet, despite this, we can study it. We can measure it. We can understand it. We can build a coherent picture of how stars are born, how they live, how they die, and how their deaths shape the chemistry of galaxies and the formation of future worlds. WOHG 64 is one chapter in that ongoing study, a particularly vivid chapter, given its size and its recent fame, but one chapter among many. There are other hypergiants waiting to be resolved. There are other supernovae waiting to be observed. There are other discoveries waiting to be made about the limits of stellar physics. The work continues. It will continue for as long as there are humans willing to look upward and ask questions, and as long as there are instruments capable of providing answers. And maybe, more quietly, the work continues even beyond that. Because the atoms that WOH G64 will eventually scatter into the large Magellanic Cloud, the carbon and oxygen and silicon and iron that it has forged in its core, those atoms will not vanish when humans are gone. They will continue to do what atoms do. They will mix with other gas. They will eventually condense into new clouds. They will be incorporated into new stars and new planetary systems. Some of those new planets, in some far distant future, might host their own forms of complexity. Some might host their own observers, beings who look up at their own night skis and try to understand where they came from. If they do, and if they are clever and patient enough, they will eventually trace their own atomic ancestry back through the layers of cosmic history. They will find that some of the atoms they are made of came from a star that lived and died in the large Magellanic Cloud, a star that we, in our small moment of awareness, call WOH G64. They will find that they are connected to it, in the deepest possible way, through the simple physical fact that they are built from its remnants. The star will be long gone by then. The supernova will be ancient history. The black hole or neutron star at its center will be drifting silently through whatever galaxy still exists at that point. But its legacy will persist, encoded in atoms, scattered across worlds that we cannot yet imagine. That is the strange and humbling reality of the universe we live in. Stars come and go. Galaxies evolve and merge. The cosmos itself expands and cools toward an unknown future, but matter is conserved. Atoms persist. The carbon in your fingertip, the iron in your blood, the calcium in your teeth, all of it has a history that stretches back through previous generations of stars, all the way to the moment of cosmic origin. WOHG 64 is now contributing its share to that ongoing story. So have countless stars before it. So will countless stars after. The next time you find yourself under a dark sky, take a moment to look toward the southern horizon if you can, toward the constellation Dorado, where the large Magellanic Cloud is visible from southern latitudes. Even if you can only see the faint cloudy glow of the galaxy as a whole, know that somewhere within it, hidden from your direct view but real nonetheless, this enormous star is shining. And know that, somewhere in the distant future, the explosion that ends its life will brighten that small patch of sky to a degree that everyone, everywhere, on whichever hemisphere they live, will be able to see. It might happen tomorrow. It might happen in 1,000 generations. The exact timing is one of the many things we still do not know. But it will happen. And when it does, it will be one of the great events of our species' relationship with the cosmos. A star we knew, a star we studied, a star we imaged for the first time in its galaxy, going out in the most spectacular display the universe is capable of producing. The light of that explosion will travel for 160,000 years to reach us, carrying with it the final message of a star that has been preparing to die for as long as anyone has been watching. And when it arrives, if humans are still here to see it, we will remember tonight. We will remember the patient work of astronomers who pointed their instruments at a small red speck in a satellite galaxy and refused to look away until they had seen what was there. We will remember that we live in an extraordinary universe, full of objects we are still only beginning to understand. And we will remember that the limits we place on what nature can produce are, more often than not, only the limits of our own current understanding. Thanks for joining me on this journey to the edge of stellar physics, to the dust-shrouded heart of another galaxy, to the boundary of what we know and what we are still learning. If this story moved you, consider liking the video or subscribing to the channel. These explorations only reach more curious minds when others help carry them forward. And remember, somewhere in the southern sky tonight, a star larger than the orbit of Saturn is shining. And scientists have just found another.